This call is now being recorded.
Okay, welcome everyone to our weekly meeting on quantum information. And this week we have Ananda, who is going to talk about what sort of change is the quantum state. Ananda is now a postdoc at IISER, and so Ananda, you can start.
Okay, thanks for this opportunity to discuss the topic of psi ontology with you. So let us begin with the question that what sort of a thing a quantum state is. So the talk will be very introductory level, and we will try to uh, capture the main conceptual points of this topic. So, quantum state is the key thing of quantum mechanical description of world, but it is for this reason it is quite surprising or remarkable that physicists do not agree upon what this thing represents actually. So there is some broad departures in the interpretation of quantum state, and it finally leads to entirely different interpretations of the theory itself. Whole formalism becomes attains different meaning to different meanings attached to this quantum notion of quantum state. So before going to the interpretational issues, we will first start with very definition, unfiltered definition of quantum state, mathematical, dry, mathematical, rigorous definition of quantum state. Okay. So any theory can be characterized by specifying the set of questions or measurements that it allows to be asked regarding the system it describes. So in that, the same thing applies to quantum theory also. But unlike classical theory, the prescription for the set of questions or answers is a bit abstract. So what you have to do is first consider a Hilbert space. For now we will consider d-dimensional finite dimensional Hilbert space, and one needs to consider the set of all positive operators, positive semi-definite operators on this Hilbert space. So take this set all E such that this holds. So we call this effect space for quantum theory. So these are the any question, in outcome question or measurement is actually n number of such operators such that they sum up to identity operator, and for each I here represent one answer of this question or one outcome of this question. So if someone declares this as the possible set of measurements, and then the theory is almost specified, apart from the compositional issues. So let's so this is the set of questions, and any probability measure on this space, suppose we take, that maps elements of this effect space to real numbers between 0 and 1, obeying certain conditions, that it will map identity operator to 1, and number 2 is it will map this kind of thing. So there is a theorem, Bush-Glesson's theorem. Originally the theorem was of Glesson for projective operators, but there is a generalization by Bush for any dimension that states that any such probability measure can be in one-to-one, can be associated in one-to-one way with density operators rho, such that mu of E is basically nothing but trace of rho.
Ananda, I have one question here. So you see, so first condition is saying that, okay, if I have an identity operator, then your probability measure has to give 1, right? And if you have a multiple EI operators, so then their summation has to be, this is a linear constant, right? Your probability measure has to be linearly connected, right? So this first one look intuitive to me, but what about the second one? Is it also intuitive?
No, it's not intuitive. Here, the second one actually is a prescription that tells, suppose E1 is E1 corresponds to one outcome and E2 corresponds to another outcome, then there is no a priori reason to associate outcome 1 or outcome 2, this OR event, to be associated with E1 plus E2. There is no a priori reason to assume that. So the second condition actually prescribes that very fact, that if you have E1 outcome, if you have outcome which corresponds to the operator E1, if you have outcome which corresponds to the operator E2, then if you consider the event where you say it is either event 1 or event 2, then the corresponding operator will be E1 plus E2, and it is for so it is a
so this is one of the assumption, right?
Yeah. So it is not a priori obvious that ORing between events should be also at the operator space should be simply addition of operators. So it's a good point.
But suppose you take a measurement M, you define a measurement M, and for that you define some EI. Okay. So for that things, I think it would be obvious that, okay, if I take those operators EI which all these operators belong to the measurement M, their summation has to be can be connected with this. For that case, because that is from the probability rule, right?
Yeah. Actually, this probability measure, when you are imposing this probability measure, you are actually keeping in mind that I am going to form my measurement as a set of operators, and that the sum of all the probability should add up to 1. And that kind of intuition is behind. But still, it is not a priori obvious that outcome 1 or outcome 2 should correspond, the operator for outcome 1 or POVM element for outcome 1 or outcome 2 should correspond E1 plus E2. This is not a priori obvious. So if we assume that, then density operator is the only option as a valid probability measure. So
great. Okay, thanks.
So this is the only the Hello.
Is this Gleason's theorem valid for any dimension or dimension greater than 2?
Yes, Gleason's theorems is actually not for all POVMs, only for projective operators, and that is only valid from dimension 3 onwards, not for qubit.
Yes.
Because for qubit we have an example of Bell model, which gives valid probability measure, deterministic. But if we consider all POVMs, then Bush has generalized the Gleason's theorem, and that is applicable from dimension 2 onwards. So
okay.
So that's why we refer to this as.
But there is already a counter example in dimension 2. So how?
That counter example is only applicable to projectors. If you include POVMs also, you cannot have a probability measure that will satisfy number 1 and 2 conditions, and also give you Bell-like deterministic probability measure. So that Bell model is confined only, that is giving probability measure only to projector operators, not POVM operators.
Okay, thanks.
So yeah. Hello.
Can you hear me?
Now I can hear.
Yeah, I'm saying let's if I try to understand in this way, let's say I'm doing a coin tossing.
Manikda, your
Yes.
voice is not very clear.
Am I audible now?
Yes, yes, yes.
Yes, audible, but yeah, okay, fine.
Yeah, I'm saying, let's say my event experiment is coin tossing experiment. So I have two events, head and tail. And now, by probability assignment, I want to assign probability to this event. And we say, okay, probability of head or tail is equal to probability of head plus probability of tail. And here we just say plus because we know these two events are disjoint. But let's say I go die rolling experiment. And I say my one event is obtaining outcome 1. Another event is obtaining outcome odd number.
Odd number, right?
So then my probability, it will say probability of getting outcome 1 or odd number is equal to probability of getting 1 plus probability of getting odd number minus their intersection.
Right.
Okay. So now for projector level, Gleason's what he does for projector level, if they are orthogonal projector, intuitively we can see, oh, these are the disjoint events.
Right.
But for few of them, it is not so obvious in general.
Right.
I can try to say in this way, but whether that brings another assumption, I don't know. That Neumark dimension, again, higher dimension, it is a projective measurement. But whether saying this, I already invoke some additional assumption, that is not very clear.
Yes. Actually, this is only just preparation and measure scenario. Whether two measurements, when we say completely equivalent, we have to also consider the state update. So whether we go to the higher dimensional charge of the Neumark dilation,
Yes.
whether they coincide or not, that is a further question to investigate.
Okay. So for the time being, we are taking this as an assumption.
Right. So, yeah. So this is the definition of quantum state. We do not have any interpretation of what these probabilities actually mean. Even up to now, it is only a mapping from these operators to real numbers between 0 and 1. Now we will go to some kind of interpretational issues. So the definition says that a quantum state is nothing but a huge list of, not so huge actually due to fiduciality, but still I will say huge list of probability distributions. So basically it boils down to how we interpret probabilities. So what sort of thing a quantum state is, this question now reduces to the question what sort of thing probabilities are. So probabilities can be broadly interpreted in two ways. One is frequentist approach, which requires us to go for operational approach towards quantum theory, and another is Bayesian personalist approach. The entire study that has been done in the ontological model framework that excludes this perspective, that has actually taken the operational interpretation and then classified among finer distinctions. But I will very briefly comment on this Bayesian personalist viewpoint, and the cubism or relative state formalism interpretation of quantum theory actually takes this point of view, and where the debate stands, whole debate stands from this point of view, we will see that. But before that, we will start with this frequentist approach. So for that, we will have to move towards lab where there is any experiment is going on, and we can abstract out the unnecessary details and confine our attention to two-stage process. One is preparation, one is measurement. And this P is a variable. There can be many possible preparations. It is a set of instruction that an experimentalist follows in lab to do something macroscopic handling of his devices. And measurement is similar a procedure, but only differs in a way that it ultimately generates an outcome at the end of a process. So, and for a given preparation, we can, and so suppose the outcome is B, we call B. So we have this PB given, suppose PM. So, and if we take all possible such probability distribution for all possible M's, I don't know why this writing is going clumsy. One second, I change my pen. This set of probability distributions, these are actually relative frequencies, and they tend to some probabilities, they tend to some finite numbers, and we interpret the probabilities that we encountered previously as the frequencies. The relative frequencies actually correspond to those probabilities. So this is a very straightforward interpretation, an interpretation that that is obvious in a lab. So so here quantum state is actually a property of a preparation. So it is a list of probability distribution for all conceivable measurements carried out upon systems emitting from that preparation. Now, quantum theory is notorious for one reason, that these probability distributions are not sharp. That means they are random. The most non-random probability distributions that it allows, it allows only for one measurement. So, so now it is a fact that whenever we come up with randomness or indeterminism, we try to see this indeterminism as kind of statistical mixture of a more refined states or things. This is what we actually do in our classical physics. And so how we interpret the whole situation, we say that, okay, we are seeing that if we are doing the same preparation and doing same measurement, we cannot reproduce the same outcome. But then we say that, okay, maybe we are not doing the same preparation. Maybe in different rounds, we are actually making different preparation procedures, because the objects that are being measured are microscopic, and there may be parameters that is not precisely accessible by our macroscopic means, and in each round those macroscopic parameters are not precisely controlled, and therefore the randomness or indeterminism is coming. So these probability distributions can be thought of as mixture resulting from statistical mixture of more refined sharper distributions. So the extreme thing is to define some states for which all the measurements have definite value, no randomness, and the observed statistics then we will think as a mixture of these definite states. So we posit a space of states which we denote by capital lambda, which we call the ontic state space, and each point here, a small lambda, these are ontic states. That means These are the real states. Reality corresponds to these lambdas, not to the observed statistics. Observed statistics comes from statistical mixing of these lambdas. Now, whenever we are preparing a quantum state, we are actually not preparing a specific point on this capital lambda space. We are preparing a distribution here. So let us call this mu lambda given phi or rho. So and due to this non-sharpness of this distribution, this epistemic distribution, we observe the operational randomness. This is the very common way of thinking. But here, if it is the operational level, there, and this is the deterministic lambdas, there is a range of possibilities. I mean, there can be less random than the operational statistics. Lambdas can be less random than the operational statistics, and even cannot be entirely deterministic also. So deterministic lambdas are an extreme case. So there can be many things in between, and one can suppose come up to here, which is less random than operational statistics, but not entirely deterministic, and say that my reality is actually corresponding to this. So there, this is upon us where we attach our reality. Someone can even attach reality to these operational statistics. So they can say that operational statistics is actually my reality, and this is one kind of interpretation of quantum statistics. It is called psi-complete interpretation. So it says that operational statistics is everything. It is you can think mathematically it is a mixture of more fundamental lambdas, but I do not attach any reality to those lambdas. One can view the quantum theory in this way also. So it is upon us how we want to see the statistical aspect of quantum theory. Now, we will consider primarily psi-incomplete models, because psi-complete model is the orthodox quantum theory. Now, in the class of psi-incomplete models, there are two broad classes that we will discuss. One is psi-ontic model, and another is psi-epistemic model. So the idea is very simple. So in every model, since they are psi-incomplete, in every psi will correspond to some non-sharp probability distribution over the space of lambdas. Now, for psi-ontic model, for any psi 1, psi 2, these patches on this capital lambda space will be disjoint. There will be no overlap. But if there is at least one pair of psi and phi for which there is a non-zero overlap, of non-zero measure overlap, then we will call that is not a psi-ontic model, it's a psi-epistemic model. Now, what is the philosophy behind this kind of distinction, this kind of categorization? Now, psi-ontic model says that this psi actually, even though it is incomplete, it still corresponds to reality, underlying reality. But in psi-epistemic model, it is not only merely psi is incomplete, psi does not even correspond to actual reality. So let us see how. Suppose I am in a psi-ontic model. So psi 1, psi 2, psi 3, these are three states for the time being. Now, suppose I vary psi, the quantum state. So if I take my system from psi 1 to psi 2, then the underlying lambdas must change. They cannot change. So if I attach reality to lambda, then the reality, I cannot say that my quantum state will change, but my reality, underlying reality can remain the same. That is not going to happen in a psi-ontic model. Whenever you change quantum state, underlying reality must change, because any two quantum states do not share common reality. But if you have a psi-epistemic model, here it is psi 1, and it is psi2. Whenever you will change your quantum mechanical description of a system, you at suppose t before 0 you say it is psi1, and t greater than 0 you say it is psi2, then you are not, it is not necessary that underlying reality, the lambda, has changed, because maybe initially the state was in this lambda state, and your description of the system has changed from psi1 to psi2, but the underlying reality, the lambda state, has not even changed. So ψ-epistemic model, you can vary the quantum states even without vary the underlying reality. So if this is the case, then it is not, it implies that my description, the psi description, this actually does not correspond to reality. It can change even without altering the reality. So this is the basic philosophy, how Harrigan and Spekkens had made this distinction between these two kind of things.
One question.
Yeah.
So in that ontic model, you have taken those disjoint psi1, psi2, psi3. Why are you taking it to be like having some intersection in psi1 and psi2? Does it have some deep meaning of
intersection? This is to show an example of ψ-epistemic model. The first one was ψ-ontic.
Okay, but
this is ψ-epistemic.
So what I'm saying that over there, why are they taken to be disjoint? Like, I'm not getting this particular point.
Oh, you were asking why I have taken in the upper diagram the disjoint, but this is the definition. Yes. Yeah, right. Yeah. This is the definition of ψ-ontic, that every probability patch on the capital lambda space for every psi and should be disjoint. There should be no overlap between each other.
But that overlap is possible in the epistemic model.
In the epistemic model. And the basic philosophy that people often say that in ψ-ontic models, psi corresponds to reality, and epistemic model, it is only mere information. Why that is what I was trying to convey, that in a ψ-ontic model, you see that you vary the psi, you cannot vary psi without varying the underlying reality, because you have already taken the stand that your reality is corresponds to lambdas, not psi. So even if it is psi incomplete, but still psi is somehow dependent on the underlying more fundamental realities. So you vary psi, you will necessarily have to vary the lambdas, underlying reality. But in case of ψ-epistemic, due to these overlaps, you can vary psi, you can go from psi1 to psi2 even without any alteration in the underlying reality. So that is the main philosophy behind this classification. Okay. Now,
but there must be at least one lambda for which even in the epistemic case you have to make the translation on the lambda level, right?
Yeah, but it is not necessary that.
Yes. If it is come from the intersection part, then this translation is not necessary.
Yeah.
What I'm saying that.
But there must be some lambdas that should change, right? It is not possible that entirely the whole thing will be remain same. That's right. True. But Harrigan and Spekkens somehow captured this as a major signifier or indication of knowledge rather than reality, because varying my description of reality, if does not correspond to necessarily correspond to underlying change in reality, then my description is not actually about underlying reality. It is only my description from prior experiences. So this is the philosophy.
Ananda, I have just another question. So what is the difference between psi-complete and psi-ontic?
Okay, psi-complete models are automatically psi-ontic because
can I think that it is a single lambda? I mean, for every psi1, the patch is only a single lambda.
Psi itself is the lambda. Psi itself is the lambda.
So if there is a multiple lambda, then I would call it psi-ontic, not psi-complete.
Yeah. Ψ-ontic model is by definition it will become ψ-ontic, but not necessarily all ψ-ontic models are complete. And more interesting will be when they are incomplete. So, and ψ-epistemic models are of course incomplete because there is no scope of overlap in ψ-completeness. Okay. So now now we have in the literature examples of both kinds of models. First, we briefly discuss ψ-epistemic model, which is a very famous model by Cochen and Specker. So what they do, it's a model for d-dimensional quantum system. So you have this block, an unit sphere, and so given a psi, the probability distribution, given a psi, the probability distribution will be like this. And given a lambda, whether phi projector clicks or not is given by this. So lambdas are any unit vector along this sphere. Now suppose this is my psi. So the probability distribution, that if you consider this prescription, the probability distribution somehow looks like this. It will be highest along this line because this theta function is 1 when the x is positive, and if x otherwise it is 0. Now and if we take the probability, if we calculate the whether it matches with the operational statistic. Oh, one thing I forgot to discuss, that that any ontological model will be thrown out if it does not corresponds to operational statistics. So let's introduce it by one explicit example, that if we integrate out over all the lambdas, and it will come up to this, and this is the basically one can calculate, this is basically psi phi mod square. This is the Born rule. So this description, this model actually reproduces quantum statistics for projective measurements. The model is precisely for projective measurements, not for POVMs. But one thing to see, that this model is ψ-epistemic, because you see that other than two orthogonal states, psi or psi orthogonal, for psi orthogonal it will be this kind of probability distribution. But if you take any two non-orthogonal state, their probability distributions will have overlap of non-zero measure. So this is a psi-epistemic model. In fact, it is a maximally psi-epistemic model. Epistemicity is not only an yes/no condition; it has a degree. But I will not discuss that degree of epistemicity here. But it is still, I will remark that it is a maximally psi-epistemic model. And this, apart from this model, there is another famous model for qubit d-dimensional quantum system, which has been generalized to higher dimensional, like Cochen-Specker model. that is the Bell model. I will write down the prescription of Bell model. Suppose we are considering this psi, we are taking this description. So now for psi, I will denote it by n vector. And in this model, lambda is actually specified by psi together with another parameter, a real number omega, which lies between -half and +half. So this whole thing now is my lambda. Now we know that for qubit we can write down projectors as sigmas as this kind of objects like plus identity plus m dot sigma, this kind of thing. So the Bell model gives this prescription that if you are in a state, lambda state, which is specified by n vector and omega, then the probability that this project will click, probability that this projectile will click is given by half 1 plus signum function omega plus half n vector dot m vector times signum vector dot m vector, and this signum function takes value 1 whenever x is greater than 0 and takes value -1 otherwise. Okay, now whether we check, so before that we take notice of the ontological state space of this model. So each small lambda is given by psi and another real number omega. So we can think of the ontological state space like this. Suppose these are different psi's, psi1, psi2, and so on, psi-n, and for each psi there is a space, there is a freedom for omega to move around from -half to +half. So omega can take any value. And each psi there is an uniform distribution over this omega. So the ontological state space is basically this unit sphere, block sphere, a Cartesian product, this -half to +half. So you see that here psi takes a part in the composition of the small lambdas. So this is why this kind of models are called psi supplemented models. That means you keep psi, and with psi you add some variable, you include some variable, and that psi together with that variable determines the complete description. And the operational psi is basically when you ignore that hidden variable omega. So let us check whether this model works or not. It is very easy. I will check it for only a very trivial case where n vector is 0 vector. That means it is 0, 0, 1, and also I am considering the projector kate 0 bra 0. That so you see that when you put these things, the entire probability p equal to 1, p is here, kate 0 bra 0, this becomes half 1 times this will become signum of omega plus half, which is equal to 1 plus 1 by 2 equals to 1, because omega is between -half and +half. So you can see that what Born rule says, the Born rule says the probability should be 1, and this model also for each value of omega, this model also predicts that for all values of omega, the response function will yield value 1. So averaging out all those 1 will give you 1. So it satisfies the requirement of Born rule. So I'll not, in general, I should check that whether this holds or not, that this Born probability is reproduced or not, that this famous result, that 1 plus half times 1 plus n dot sigma n dot m vector, and it is a trivial textbook material to see that this actually holds for this model. Now, in the paper of Harrigan and Spekkens, there has been a remark, and there has been a theorem also, that this kind of the psi supplemented models are all psi-ontic models. The reasoning is plain, simple. Whatever we have actually discussed, that for every psi, you have a space for omega, where omega can vary. Psi 1, psi 2, psi 3, psi 4, psi 5. And since for every different psi, this is completely different region, so we have disjointness for every psi, and that's why it is psi complete. They even introduce this kind of implication. Psi supplemented implies psi-ontic. But what one can check here, whether this implication is reliable or not, one should check that for any two pair of psi 1 and psi 2, varying omegas, can we find here 1 omega for psi 1, omega 1, and here 1 omega 2 for psi 2, such that all the response function, that probabilities for all observables, for all projectors, whether some projector will click or not, for this psi 1 and omega 1, and is equal to probability whether this projector will click or not, given this psi 2 and omega 2. This is for all projectors P. If this holds, this kind of thing happens to hold, then it is not very reasonable to say this model is a psi-ontic model, because you have this is your description as psi 2 omega 2, and this is your description, this point is psi 1 omega 1. Of course, as a set theoretic point, they are two distinct points, but from reality is what gives you all the values for all observables, that on that ground they are completely same. They do not make any different prediction. So even if your psi constitutes the mathematical, it takes part in the mathematical constitution of your small lambda, but still they can lead up to completely same ontic state for two different omega 1 and omega 2. So that is why it is arguable, sufficiently arguable, whether Bell model is at all a psi-ontic model or not. This disjointness is deceptive in that sense, that we can find points here which are basically same. So if this is the logic of disjointness, then I can take any ψ-epistemic model and relabel same points in different psi's with tagging that psi and say this is my different point, and this is that is I have got a psi-ontic model. So, and the further question is whether is this specific to Bell model, because all the known psi-ontic models are all actually psi supplemented models, and whether this is specific this kind of feature is specific to Bell model or not is worth investigating. Whether this kind of thing should occur irrespective of the model, independent of the model, is also worth investigating. Maybe it's not only specific to Bell model, or rather Bhowmian mechanics is also psi supplemented model. There you have the wave function together with the particle position. So it is worthy of investigation whether this kind of things happens there or also or not. So
Ananda, we have a questions from Sahil. So he's asking, can you answer why these 2 points are same?
yeah, one has to calculate the response functions, values of response function for all projectors, and from there one can simply conclude that these 2 points are same. I mean, my definition of an ontic state is that it captures, if this gives deterministic value, it gives 2 ontic states will be same if they give same value to all observables. So if I see that 2 different kind of points, suppose psi omega and psi prime omega prime, they look different, but they give clicks all the projectors in exact similar fashion. Then the response function for all projectors give the same value. Then I have no reason to differentiate between them. I have no reason to say this is this.
That means, are you talking about equivalence classes?
It's not even equivalence, it's identity.
What I'm saying is that because although they look different, because they are giving the same outcome for all projectors, you are saying basically they are the same state. So it is actually kind of an equivalence relation that you are forming, and then you are a representative of that equivalence class.
Yeah, you can state that also, but I will prefer not to use the term equivalence also. I will prefer identical ontic states, just has been relabeled cosmetically by this kind of state space construction. So
I am calling it to be equivalence classes. That is because you can get another psi double dash and omega double dash, which gives you this.
Right.
It's a class.
Right.
Yes,
One
that is what
can
I
have in that respect, that's an equivalent class. Where all of this lambda 1, lambda 2, or lambda 3 will give same response for every projectors. So you were right in that sense.
So actually, actually operationally we define our state like equivalent class. So what you are suggesting, even that should go for ontological thing only. If there is no operational difference, then why are you call them different?
Right.
As a set theory mathematically point, maybe they might be different, but they doesn't carry any operational difference.
Right.
So they are all equivalent.
Right. There should be some reason, at least sufficiently reasonable reason, to call them different lambda, different ontic states. So which is lacking, and that's why whether this implication that supplemented models are automatically ψ-ontic is worth reconsidering. So this is one thing. So let us move on.
There's one more question. So is this similar problem
that is on. I don't know. I have to check. We have to check that. In fact, it is worth investigating that whether this phenomenon, this thing, is a model independent feature or not.
Understood.
So can we get rid of this epistemic loop between different branches of different psi branches? So that is worth investigating.
This overlap definition is a problem.
Yeah, I am right. I am considering this aspect up to now from this overlap interpretation of epistemicity. So that's why one has to change in the formalism at least one thing, whether you change your modify your definition of epistemicity so that you can still call this Bell model a genuinely ψ-ontic model, or you have to reconsider. If you do not change there, you have to reconsider what you should call Bell model, ψ-ontic or ψ-epistemic.
So, but I'm saying if in your model, let's say S depends on omega, but doesn't depend on psi. That case problem will be less.
Yeah.
That way
In Bell model, the response actually depends on psi and omega both. You need both.
but I'm saying in potential spectrum model, it doesn't depend on psi.
Right, right.
So that's
Actually,
that's it.
If you define your ψ-ontic model in that way, then I have no problem. Then one should have no problem. The Bell model will be, of course, a ψ-ontic model if your definition is that. But the philosophy that we earlier discussed in this here, that the overlap basically corresponds to, I mean, ψ-onticity. That if I change the description, quantum mechanical description, that necessarily implies change in the underlying reality. In that, if I take that kind of philosophy, then I think this non-overlapping supports are a good choice for ontic definition of onticity. So in that sense, this motivation and definition is appealing enough. So rather than I should rather prefer not to change the definition altogether, but to raise the status, update the status of Bell model or any psi supplemented model for that matter. Okay. So now we will move on to a very important result that actually gave a very spark in this field. That is called Pusse-Barrett-Rudolph theorem. The theorem is very simple. The argument is very simple, but still I will make that 1 second. So they give an argument. PBR gives an argument that under some constraint, under some assumption that that implies impossibility of epistemic interpretation. So here is a very simple thought experiment. So you have two preparation device. One preparation device is this. It emits some state, either Ket 0 or Ket plus, and another preparation device is this one. It emits some state Ket 0 or Ket plus, right? And you have some measuring device here. Your job is to discard the joint possibilities. What are the joint possibilities? Joint possibilities is suppose this is A, this is B. Joint possibilities are, this one is a joint possibility, this one is a joint possibility, this one is a joint possibility, this one is a, these are the 4 possibilities. One has to discard in each round one among these 4. And if we take an epistemic view, then you see that these 2 states are non-orthogonal, and in the lambda space Suppose this is the ontic support of Ket 0 and this is the ontic support of Ket plus. So there is a non-zero overlap. And similarly here also for the system B also, this is for Ket 0, this is for Ket plus. So if now the assumption part comes, if two operationally uncorrelated preparations, this is an operationally uncorrelated preparation, if they also are uncorrelated at the lambda level, so mathematically if we write this, suppose this is lambda 1 and this is lambda 2, so lambda 1 and lambda a, lambda b, lambda a comma lambda b, given this psi 1 and psi 2, psi 1 psi 2 is tensor product. If we assume something like this, not only existence of this but also this kind of factorization, that means this is an operational preparation and this is this probability distribution signifies the ontological preparation, and if corresponding to operationally independent preparation the ontological distributions are factorized, that means independent, then one should or immediately conclude that there will be some run, at least with some q, suppose with non-zero probability, that here lambda a will come from this overlap region and lambda b will come from this overlap region. Both of lambda a and lambda b has come from overlap region. This is if you take this assumption, because otherwise you have to ensure that whenever lambda a comes from this overlap, lambda b does not come from this overlap. But this kind of constraint is precisely what correlation means. So correlations uncorrelated means there should not be any constraint, where there should not be any dependence between lambda a and lambda b emission. So there will be some runs with finite probability where both the lambda a and lambda b has come from overlaps, and it immediately implies there will be some runs where I will not be able to rule out any one of them, any one of these four. But this actually contradicts quantum mechanical prediction, because quantum mechanics allows measurement, an entangled basis measurement. Suppose, let me an entangled basis measurement. If I measure 0, 1, I will not writing the normalization factors. 0 minus and okay, if it is a projective measurement, one can verify. This is the basis basically. So if for each outcome I can get rid of one, so at every run I can get eliminate one. So this kind of task is now called anti-distinguishability task. After PBS theorem, this has emerged as a interesting quantum information theoretic task, which is a very weaker version of quantum state discrimination, where among n possibilities you eliminate n minus 1, and here among n possibilities you are eliminating only one. So that is possible here at every run. So quantum mechanics says that your q should be 0, but epistemic interpretation says that q should be strictly greater than 0. So this is contradiction. So if you need to have an epistemic model for quantum theory, you have to ensure whether your two independently prepared systems ontic states are uncorrelated. This is a lesson from PBS theorem. So how much time do I have left?
You can wrap up in 5 minutes, I guess.
Okay. So this is Pavier's theorem, and another thing I will just state that this epistemicity has a connection with local realism also. The first connection has been shown by the Harrigan Spekkens paper in a very beautiful proof that any ψ-ontic model will be necessarily non-local, non-local model. But I'll not go to the proof of this because this is very simple and one can check the paper, and simple proof, very simple proof. We will rather comment on the converse of this statement, whether locality has some connection with ψ-epistemic models or not. So I will give a very short argument, thought experimental argument for this connection. Suppose I have a copying machine, unitary copying machine. It of course does not copy non-orthogonal state. It copies orthogonal states. Suppose it copies 0 and 1. So this is my unitary. Makes 0 0 0 and 1 r goes to 1 1 1. So if I have this unitary, and we make an assumption which PBR also assumed, that for any product state, PBR assumed that we have this kind of probability distributions this kind of. They also assumed a second step, that this gets factorized, right? We are not, for our argument, we do not need this factorization part. We need only the existence of these probability distributions. So for any product state, the ontological support of any product state does not contain any non-local ontic state. Whatever it contains, it can be decomposed in terms of lambda of system A, comma lambda of system B, this kind of thing. So we have an unitary which has 3 port, this unitary, and 3 output port, and we have this kind of this is ontic support lambda r, lambda 0, and this is some output state. And suppose I prefer GHG local measurements here to check Bell-Marmin violation, which is one of the local realistic inequality which quantum mechanics attains the algebraic maximum. So unlike CHSH, where it stops at 2√2, but the algebraic maximum 4 for Bell-Marmin violation, quantum mechanics attains this. Now we will utilize this fact to conclude something interesting. So suppose we have this thought experiment, and we know that whenever we feed gate 0 at the operational state input, we get at the output gate 0 tensor 3, which is local, whose ontic state space, whose ontic support will be local. And now if we have gate lambda plus, okay, and if we assume that lambda plus has some overlap with lambda 0, then we must say that if we consider all the runs of feeding with gate plus, then at some runs lambdas will come from this overlap region, and the machine will think that it is being fed with lambdas from the support of gate lambda 0. So capital lambda 0. So machine will prepare on local ontic state, because when gate 0 is operationally fed, the output ontic state, since the output state is product state, its ontic support does not contain, our assumption says its ontic support does not contain in non-local ontic state, the output will be local. So whenever you are feeding the first input port with gate plus, in some runs you are actually preparing local lambdas at the output, because in some runs it will come from this overlap and the machine will treat it as gate 0, gate R, and it will operationally produce a product state. And our assumption is whenever operational state is product, we have ontological ontic states are local. So at some runs for gate plus, even if you feed gate plus, at some runs there will be locals, and if you take the entire all the runs and average, you will never get the algebraic optimal for any local realistic inequality, here in our case Marmin inequality. But what quantum mechanics predicts is if you feed the first input port with gate plus, at the operational state will be a GIG state, simply by the linearity of unitary dynamics, and you have local measurements here in 3 ports where you can get the obtain the algebraic optimal. So it is in contradiction with quantum mechanical. The quantum mechanical prediction is in contradiction with this kind of overlap kind of interpretation. Even partial overlaps are not allowable. Here we have only eliminated overlaps interpretations for states like 0 and gate plus, not for arbitrary psi and phi. 0 and gate plus are special because they are states of the form where their inner product mode is 1/√2. The proof, if extended for arbitrary psi and phi, it only gives a bound on the overlap, not like PBR. It does not eliminate the overlap altogether, unlike PBR, but it gives some bound. But for this kind of overlap, quantum overlap for 1/√2, it eliminates, it establishes 0 overlap. So non-orthogonal quantum states can have, must have the 0 overlap in any model where product states, whatever be the preparation procedure of a product state, it is the ontology does not contain any non-locality. So it ends our discussion of connection with local realism and epistemicity. Lastly, I will comment on the Bayesian perspective. All these discussions have so far contained this frequency and frequentist approach. The probability measure has been interpreted as frequency of outcomes obtainable in lab, but with the very ongoing research on Bayesian probabilities. So I will just quote Bruno de Finetti, the one quotation, which says that probabilities are not to be taken as something, some property of the object. Suppose I assign some probability for some observable, some property of a system, some probability, even if it is 1, probability 1, it is my expectation. It is the quantification of my expectation of its future behavior. It has nothing to do with the system in principle. So what Bruno de Finetti suggests here, he says that the abandonment of superstitious beliefs about the existence of phlogiston, the cosmic ether, absolute space and time, or fairies or witches was an essential step along the road to scientific thinking. Probability too, if regarded as something endowed with some kind of objective existence, is no less a misleading conception, an illusory attempt to exteriorize or materialize our actual probabilistic beliefs. So we started with quantum definition of quantum state, and from that we reduced the question of meaning of quantum state to the question of meaning of probability, and then we moved on to the frequency meaning of probability. But there is standing another meaning, interpretation of probability, where probabilities are simply our personal beliefs, and we can share our beliefs and make up an story about external world. That does not by no means avoids the existence of external world, but we have an external world, we can intervene on the world and expect its responses. And from our prior experiences, we have expectations for possible responses. And probability is just quantification of that. And science is basically a method of assigning or better assigning or quantification of this expectation. So this is the point of view that cubism or relative state formulation, this kind of interpretations take. From their ground, even if you have lambda which gives probability 1 to everything, they will not say terms like reality. They will say determinism, that it is something that helps us know everything, but they will avoid terms like reality, because it is ultimately, even probability 1 is our belief, a belief for which Marvin says, I can bet my life. So this is the so the whole debate is actually residing in this part. If you go to this part, the debate dissolves. So this is I think we can finish here.
Thank you, Anand, for this very nice introduction to ontological models and interpretation. So, are there any questions right now? If you have any question, you can unmute yourself.
Yeah, Anandam. Yeah, regarding this last part. So can I see it this way that okay, this Bayesian that reality exists. But as an observer, yeah, nature reality exists. But as an observer, we are trying to give a description of the reality.
Actually, what cubism sees science as a way, how cubism posits, first of all, it posits an external world. Yes. And there are many users of quantum theory, or many users of science altogether, and science is basically synthesis of our prior experience, from which we attach expectations, assign expectations to different kind of responses in reaction to our intervention to the world. So measurement is basically one very simple kind of intervention that we make on the world, the quantum measurements, and the bound probability is one science, is part of that whole big science that guides us how not to fool ourselves in assigning likelihood. So ultimately, that Dutch book argument that says, for the quantum Dutch book argument, that if you take your possible propositions as the quantum project correspond to quantum projection measurements, and then you apply Dutch book argument, you will see that all the axioms of Gleason's theorems are automatically being satisfied, and from there you can derive rho is the only possible assignment of expectations. So in that way, quantum probabilities can be completely derived as Dutch book argument probabilities. So you are in a betting game and you don't want to lose, you want to be consistently betting. So then you will have to actually bet in accordance with bound probability or rho. So
yeah, that's what I'm trying to say, that it's objectively the nature is there, it already exists, but as an observer, we are trying to give a description. Now, in this description, there might be some part of subjectivity.
Yeah.
So it's a kind of, but I'm not saying it is everything becomes subjective. Some part is objective, some is subjective.
Of course. Experiences are subjective, but experiences are personal, but it is conveyable to others. And from this even if this method of convey that language, that scientific articles, whatever we do, we make up a general story, common objective story for all of us about this external world. But but that does not rule out the personal part, and of course also does not rule out the existence of this external world, because otherwise cubism does not make sense without the existence of the external world.
Because that will become the solipsism.
Yeah.
But
The whole point of cubism is
what is the fundamental criticism to the cubism? Because I'm saying cubism, I'm trying to how I understand it, is a very progressive way of seeing all the interpretation.
Yeah.
But what is the fundamental criticism people try to raise who are non-cubists?
It is from the gravitational perspective, because I think the Everett's interpretation, the advantage that Everett's interpretation provides for many researchers in gravity, quantum gravity, that is not a priori obvious in cubism. But that's still not still early to comment that it's against quantum gravity framework, possible frameworks, but that objections actually more from gravitational perspective, more from Everettians.
And another okay, can we continue this discussion? I don't know that Som, if you want, you can stop there.
Or maybe I will just ask if anyone else have any questions. Otherwise, we can continue with your questions. So, does anyone else have any questions at this point? I guess no. So yeah, maybe you can continue the discussion, and we will
continue the recording, or do you want to pause it?
What do you prefer, Manikda? What do you prefer? Should we continue the recording, or?
I am fine with anything. I'm saying since
then okay.
Long, that's the answer.
Yeah, it could be long, but that is not the main problem. This is an interesting discussion is happening, so it is okay if we'll keep it as a record.
Yeah. So Ananda, what I'm trying to say now, I'm starting from very old. It's going to be philosophical. So you see, let's start from the Zeno. So we know rest and motion, no? You have to accept both are there. From rest you cannot obtain motion, no? Both are there. You have to assign a means. You have to posit a prior.
Right.
Otherwise, the world will be a very boring world. Everything is a snapshot of something.
Right.
But that dynamics is there that makes the world interesting.
Right.
But I'm saying on this ontological formalism, you see, dynamics is not playing the role. I'm saying dynamics is not playing the role in a sense where I'm saying, okay, how given a dynamics, ontology will change on fixed state. That is not my question. I'm saying dynamics fundamentally should play the role when I'm trying to build ontology. That is not, because it's missing somewhere. So all the ontological aspects, kinematical aspects.
Yeah. They are primarily focused on the preparation measurement setting. The dynamics is so far it is relatively overlooked. What are the dynamical implications?
I'm not saying like this hardy kind of thing. So if I have already this lambda, if I give a unit array, then lambda thing, this is not what I'm saying. Dynamics is a basic element here in the ontology.
Of course. I mean, so are you suggesting that that dynamical dilemma that appears in Wigner's friend kind of scenario?
That is enough. That is not very precise thing. What I'm trying to say, like I say, okay, so some lambda exists, reality exists. It's a property, it's a dynamic. Reality means It is raised as well as some dynamics is something observer independent, something that is should be the should play a role or something.
Okay, okay, I understand. So
Maybe Shumit want to
Yes,
say something.
Shumit wants to say something.
Yeah, so Manikda, so as you are saying about this dynamics and statics thing, so as we are discussing the abstract thing, so should we, there is any particular reason for which we will always consider this dichotomicity of the world, like black and white and yes or no?
Yeah, that's what I'm saying, Shumit. That is a very good point. That's what I'm saying. I'm saying you go to Zeno. Now, Zeno, if something is raised, how it is having dynamics, kind of.
Yes.
How will you explain that? So then there is a philosophically I have escaped that okay, because rest and motion both are contradictory. At every moment, the system possesses both. Sometimes rest is predominating, sometimes dynamics is motion is predominating.
Yes.
It's a kind of dialectical standard. I'm saying in my ontology, what should play?
But see, say when you have this static, only then you have dynamics, right? So I am just opposing this point of view that when you define your static, only then you have something dynamic. So when we are discussing these abstract things, so should we not go out of this dichotomicity of our mind and consider something more general? Like if cubism is one like valid abstract candidate, then
But cubism is so far, as far as I understand, cubism is so far at very operational level. Their ontology is not yet there. When they are trying to build on, give the ontology under cubist, and they are trying to bring, I heard from someone then, Christopher Cook, they are trying to think that how to bring ontology in the dynamics, how to bring dynamics in the ontology. Because for cubism, cubist, ontology is not yet known. It is the operation of so far.
yes.
That's what I'm trying to say. But what you are saying, that I completely agree, that why this dichotomy? I'm saying even that is the next goal. I'm saying everywhere I am seeing only this kinematic part also. Dynamics is playing a fundamental role in ontology. That is okay. How I want to see that is also not very clear to me.
Right.
But Manikda, so I mean, I don't understand the Bayesian perspective, but even then, whatever has been discussed today, so based on that, does it mean anything like ontology in Bayesian interpretation? So because although there is a reality or some external world, you in your description, you are always going to mix some real description and some objective and some subjective description, right? So in that sense, what is the meaning of ontology then? I mean, then ontology does not mean only about some objective description, no?
Yeah, but they are trying to exactly that part is there. That in Bayesian, that subjective part, objective part, that dichotomy is there. It is a dialectical kind of thing. But they are probably they will try to identify some dynamical quantity which is the objective nature of this, objective fact of the nature. Maybe not clear. It's also not very clear because it is not properly formulated.
Yes. Maybe we can invite some Bayesian theorist in our discussion later, like at some point.
That will be good.
Actively on this thing. Okay. So are we going to end the meeting here or?
Thanks, Ananda, for nice presentation.
thanks.
Yeah. Thanks, Anando. And okay, so I guess we can stop the recording now and end the meeting.